As a statistician, I'm often called on to do consulting, whether for individuals or for companies or even for nonprofits. And so today I'm going to take you along with me. We're going to do a consulting gig together. I might even pay you a little bit. Let's suppose we've been hired by a large metropolitan city, and they want to know whether they should build a new hospital to meet the needs of their residents. And so you and I have been tasked with developing a survey to give to the population to better understand their emergency room demands so they can plan for appropriate number of beds. Now, why is this important? You've probably been to the hospital before, maybe even to the emergency room. And what I hate when I go to the emergency room is waiting. Everybody there is sick, including me. And so when I get there, I want to get to a bed, I want to see a doctor, and I want to get well so I can get out of the emergency room. Sometimes I even call the ambulance, even if I could drive myself, just because it's like VIP access to the back, but don't tell anybody. All right, so how are we going to collect data so that we can give the city a response and tell them the demands of their residents? Well, let's suppose we sample 1,000 residents and we ask them, hey, how many times have you visited the emergency room in the last year? And we're going to record that data. In fact, we record that in the number of times that a person has visited the room, and our data set goes from 0 to 59 times in a year. That was a poor sick person. Now, the counts for each visit are going to be given in the vector that we label counts. And the vector visits is going to repeat each time for each corresponding count. Let's look at how we do that in R. Here at the top, we've assigned times to the number of times that people in our sample have visited the emergency room. In this case, that ranges from 0 to 59. Counts is telling us how many people visited to that corresponding time. So for example, 49 people visited no times this past year, 51 people visited once, 50 people visited twice, and so on. Draw your attention all the way to the end of counts, and you'll see where there's one person that visited 58 times and one person that visited 59 times. So now we have to pair up the number of times with the number of counts, and we do that to assign visits. This is going to be our sample. So we're going to assign counts to their respective times. Now, we often look at histograms in this course, and a histogram of this particular data is really going to show us not just the shape of the distribution, but also give us an idea of what the demand might be in the emergency room. So let's look at a histogram. Here's our data. Skewed a bit, and you see that it's pretty clustered around very few visits in a year, which is a good thing. But notice we do have some spread in that data where we go out to, as you knew, a maximum of 59 visits. So what do we want to get from our sample? We've only sampled 1,000 residents, and this isn't everyone in the city. How are we going to get a precise estimate of the mean number of visits per each resident? Well, we know we can compute the sample mean of our 1,000 residents, but that's just one estimate. It'd be great if we had more money. We could do more samples. Maybe we could sample 10,000 residents to really get a good idea. But we've only got this data set of 1,000. What are we going to do in this case? In particular, what we really want to know is how close is our sample mean going to be to the true mean number of visits? What we don't want to do is say, hey, if you've got 30 beds in the emergency room, you're good to go, and they're packed every night with 50 people that need help. So we could look at different samples of residents and their average number of visits, and we could look at how that estimate might change. Maybe if our sample size was 10,000, we could try to estimate that. Let's, in fact, investigate how the distribution of a collection of sample means is going to change as we change our sample size. And we don't have to collect more data to do it. Here's what we're going to do. In R, we're going to write a function. Call that function mean.age. And that function is going to take in a number n. So now we want to do 1,000 trials. And that means I'm going to sample from our data 1,000 times. Now, because we're doing a random sample, the output will be slightly different every time we run it. So if you're following along in our studio, the values you get will be slightly different. I've created this function called my.samples, which creates a matrix of the number of samples that I want to take. Here I want to do a matrix and I want to sample from my visits. The size of my samples is going to be the n that I specify times the number of trials. For example, if n is equal to 1, then my size would just be 1,000. N equals 2, my size is 2,000, and so on. Replace equals true means that I'm sampling with replacement. So if I sample a person out of my population, I throw them back in before I pick the next person. Now this means function, I've called means to take the mean of each of my sample. So at each trial, I'm sampling from my data and I want to take those means and then I want to store it in the vector mean. What we're doing here is called bootstrapping. This function mean.age is going to do 1,000 times of the experiment of taking a sample of size n at random with replacement from our data set. In a way, what we're doing is like treating our sample of 1,000 as the population. So if these 1,000 people were the population, I'm just going to keep sampling from them and taking the mean and then look at what that mean looks like. Now, X bar is going to be the sample mean of the visits of n people drawn at random with replacement from our data set. So it could be that somebody shows up in there a couple times. Now for each of those 1,000 trials, I'm going to calculate the mean. So I'm going to have 1,000 sample means returned as a vector in my vector means. If I do mean.age of say 1, then what this is going to do is draw one single person out of my sample and tell me the sample mean of that n person, n equal to 1 in this case. But it's going to do that 1,000 times. So that's just like taking a random sample of one person 1,000 times. Let's look at the histogram of mean.age when we just sample one person out of our population or out of our sample 1,000 times. Notice here, your mean.age of 1 has about the same distribution as our original data set. This makes sense because we're taking one person out of our sample 1,000 times. Now notice we're sampling with replacement. The reason we're doing that is, let's say we weren't sampling with replacement and we sampled one person 1,000 times, we would just replicate our original data set. So bootstrapping is meant to help you use your sample as a population. So that's why we sample from replacement when we do it. What happens if now we sample 2 people from our population? So now what am I doing? I'm taking my original sample of 100. I'm taking 2 people out at a time, and then I'm taking their average number of visits and I'm storing it. That's one value. And then I do that again. I sample 2 people out of my population, take their average and store it, and do that 1,000 times. That's what you see in that first histogram, the mean of 2 visits. Notice how when I sample 2 people and take their average, our histogram shifts a little bit, moves over toward the right. What would happen if we instead sampled 10 people? Right? We've got that original 1,000. We take 10 people out, take their mean, and store it. And we do that 1,000 times. Do you see how our histogram is actually starting to move a little bit? Almost like a shapeshifter. Let's increase our sample size to 20, and now it's probably starting to look like something that's really familiar to you. So we're taking 20 people out, we're sampling them, taking their mean, and storing that value, doing it 1,000 times, and here you see the histogram of that. Now notice how the mean age for a sample of size 20, done 1,000 times, compares to the original histogram of our sample of 1,000. We shifted that distribution over by looking at the means. All right, why stop at 20 when we can do 100? Take 100 people out, Take their mean, store that 1,000 times, and here's the histogram that you get of those 1,000 mean values. Now it's really looking normal. But I wouldn't want to stop at 100. Let's just do 200. What the heck? Look at this shape of this histogram. I mean, this histogram is looking really nice, almost symmetric in a way. So when we take 200 samples out and take the mean and plot that 1,000 times in our histogram, we've almost effectively created a normal distribution. Let's plot a histogram of each of those 6 means to see how those distributions changed as we increase the size of samples that we took from our sample population. Notice here, our histograms are starting to get not only narrower, but also more bell-shaped as we increased our sample size. You see in the upper left corner, when we had a sample size of just 1, that shape looked pretty much like our underlying population. It was skewed to the right. And then notice as we took a sample of size 2 and calculated that mean, we started to move a little bit toward the right. A sample of size 10 and then a sample of size 20 starts to really get concentrated. You see the normal distribution coming out. And notice when you get up to a sample of size 200, not only are we nicely normally distributed, but notice too, our spread of that normal distribution is super small. Those plots are all on the same axis so that you can see how the spread is also changing over time and compare their standard deviations visually. So we see from the histograms that the distribution of the sample mean gets narrower and narrower as n increases. In other words, what our variance is doing, it appears to be decreasing as that sample size gets larger. Well, we could see if there is some functional relationship between the variance and the sample mean and the sample size n. In fact, for each of those mean ages that we took, 1, 2, 10, 20, and 100 and 200, we could also calculate the variance and plot those as well. Here's a function we're going to call vars, where we're going to create a data frame where we calculate the variance of each of our samples. So the variance for our MA1, our MA2, all the way out to our MA200. So this is where we actually took the sample and had the histogram. Let's look at those variance values now. So notice here, when I was only picking one person out, my variance is 93, slightly over 93. But notice my variance almost gets cut in half, less than half, when I take 2 people and average those 2 people. When we move up to a sample of size 10, our variance goes all the way down to around 9.5, and a sample of 20 decreases our variance to around 4.5. And look what happens at 100 and 200. Our sample variance is less than 1, at 0.94 and 0.45. So why is it, do you think, that the variance is changing so dramatically as our sample size increases? And what might that relationship be? Well, we could actually plot the variance of each sample, the sample size versus the mean. And maybe we could sort of see, is that some functional form that we could use to understand this relationship? So check out this plot. Notice you see these red dots are the plot of our variance, and it's decreasing. It's actually decreasing according to a function 1 over n, so 1 over the sample size. In fact, the variance we can prove is proportional to 1 over n. So not only is our distribution getting narrower, the shape starts changing. It's going from being skewed to now becoming symmetric and bell-shaped, much like the normal distribution. But how could we test whether our distribution is close to a normal? Yes, I think I heard you say a QQ plot. Yeah, I know it's your favorite. We're going to do that again. In fact, we can compute the QQ plot for every one of our samples, all 6 of them, and see if those compare to a theoretical normal distribution. We've done this before, so I know you could do it in your sleep, but let's look and see what we get when we do that. Okay? So as a reminder, if the points on a QQ plot fall on a straight line, this tells us that our sample data are consistent with our proposed theoretical distribution. And in this case, it's a normal distribution. So we really want to know, is it the case that our underlying sample could be normally distributed? In R, how might we do that? So that first command is just giving me a pretty way to look at all 6 of those plots on one slide. So I don't have to keep going back and forth to look at them. So that command is par mfrow equals C, which means combine 2 and 3. So this will give me output that has 3 plots on the top row and 3 plots on the bottom row. So I can look at them consistently. And here I want to take the QQ norm of my MA1 sample, my MA2 sample, all the way out to my MA200 sample. Now we know what those original distributions look like. And so we saw how they started to approach normality as the sample size increased. But let's see if the QQ plot actually confirms that. Here is the QQ plot for each of our samples. Notice that the one in the upper left corner for our original data appears to not really be normally distributed. It's fallen way below, almost like it's got like a gangster lean in it somewhere. But as our sample size increases, our line appears to get straighter and straighter and straighter. But we've talked about making these visual bias judgments when it comes to QQ plot. And we know what we can do to test to see if it's really normally distributed or not. Do you remember what that was? Shapiro-Wilk. Absolutely. So the Shapiro-Wilk test is a normality test. And this is going to tell us whether or not, yes or no, with statistical backing, our distribution actually comes from something that's normally distributed. All right, so let's do the Shapiro test on our MA1 to MA200 samples. That function in R is just Shapiro.test of MA1 and then of MA2 all the way out to MA200. And do you remember what your p-value needs to be? Greater than 0.05. That's right. So greater than 0.05 is a good thing. That means that our data is normally distributed. Anything less than 0.05, we probably don't have normal data. Let's look at our Shapiro test for each of these samples. All right, here we go for our sample of size 1. And notice we've got a p-value super low. When you see 2.2 e to the minus 16, that's R's way of telling you is 0. So that first data set is not normally distributed. And we can sort of look at that and tell. What about a sample of size 2? So again, our p-value, super low, but not quite as bad. Notice we had some improvement, even though it's effectively 0. A sample of size 10? Well, now we're getting better. A p-value of 0.002. Still not normal, but you see where it's moving in that direction. What happens with a sample of size 20? Ooh, well, that particular sample actually didn't do as well as a sample of size 10. Notice our p-value actually goes lower. Now, this could be expected because of the randomness of our sampling, right? It could be that we had a better data set at 10 than we did at 20 because we're sampling randomly and with replacement. But look what happens when you take a sample of size 100. That p-value jumps to 0.48, confirming that you finally reached normality. Likewise, a sample of size 200 is also normal, jumps to 0.29. So what we're starting to see is that our mean has a distribution. It has a shape, and we call that a statistic. A statistic is a value that we can compute from the data. In our example, our statistic was the average number of ER visits. Now, is this average number a random variable? Well, remember, what is a random variable? Well, it's a number that we associate with the outcome of an experiment. We know that it has to have a distribution, has to have a mean, has to have a variance. And so because data constitute a random realization of an experiment, every time we rerun the experiment, we might get a different value for our statistic, just like we saw in our example. So in fact, a statistic is a random variable. It has a distribution, it has a mean, and it has a variance. Now we've seen empirically from our data that the sampling distribution of the mean appears to approach a normal distribution, at least for ER visit data. But does this happen in general for any distribution of data? Or is it just for data when you go to the emergency room? Well, by now, you may have discovered that in the field of statistics, it's rarely possible to collect all the data from an entire population. which is why we did bootstrapping in this example. But instead, what we do is we gather a subset of data from a population, and then we're going to use statistics for that sample to draw conclusions about the population. Now, the two most common characteristics that we use to define a population are its mean and its standard deviation. And when data comes from a normal distribution, we immediately have an idea of the data's shape. We know the mean tells us the center, and the standard deviation tells us the spread. Now, this is where the central limit theorem comes in. The central limit theorem is fascinating because it tells us that no matter what your population distribution looks like, your distribution of the sample means will always approach a normal distribution. I think about the central limit theorem when I think about my kids, and I watch them running around and they're acting crazy, and somehow I think no matter how weird they are or crazy they are, they're going to approach the perfect normality of their mother when they grow up. So the central limit theorem officially is defined as follows. Let's let x1 out to xn be a random sample from any distribution. Normal, Poisson, pick your favorite, Weibull, exponential, any distribution with some mean mu and some variance sigma squared. Then as the sample size increases, here's what happens to the mean. X bar is going to eventually follow a normal distribution with a mean of mu and a standard deviation of sigma over square root of n. Okay, now don't miss this. We've started with a random sample from any distribution. We haven't limited ourselves to the normal distribution. We haven't made any other qualification, just any random sample from any distribution. And as that sample size gets larger, the sampling distribution of the mean is gonna look normal. And this is exactly what we saw in our example. Now, at first, this definition might be a little bit intimidating, but don't worry, because all the central limit theorem is saying is, as our sample size increases, any distribution, whether it's normal or not, is going to have a mean that tends to behave normally. Now, because the normal distribution occurs so often in real life, and it behaves very predictably, right? We know 68% of the data is in one standard deviation, 95% is within two standard deviations. So because it's so predictable, this distribution is actually the foundation of statistical inference. Another cool thing you can do with the normal distribution is approximate discrete distributions, in particular, the binomial. We talked about the binomial before, but let's bring it up in this example and see how it connects to what we just learned today about the normal distribution. Let's suppose each person in a 3,000 person stadium has a 60% chance to be rooting for the home team. We want to know what's the probability that, say, more than 1,850 people are rooting for the home team. So let's define X as the number of home team fans in attendance. We're back to the binomial. We know that X follows a binomial distribution, right? Because it's two options. Either you're in attendance rooting for the home team or you're in attendance and you're not rooting for the home team. Total sample size is 3,000. The probability of success or rooting for the home team is 60%. Do you remember the expected value for the binomial? N times P. In this case, 3,000 times 0.6 or 1,800. And our variance, remember, is N times P times 1 minus P, which gives us 720 when we multiply 3,000 by 0.6 by 0.4. We can take the standard deviation of that, which is the square root of 720, to get approximately 26.8. So the probability that X is greater than 1,850 is equal to, all right, we got a sum over K. K goes from 1851 up to 3,000. 3,000 choose K times 0.6 to the K, 1 minus 0.6 to the 3,000 minus K. All right, so, hey, I think that would be a great homework assignment. Go ahead and work it and then email me and let me know what you get. But seriously, we wouldn't want to solve this using the binomial distribution. It's too tedious. But what we can do is approximate it with the normal distribution. For the binomial, we want the probability that, say, x equals k. But remember, the binomial is discrete, and the normal distribution is continuous. So we have to approximate it. For the normal distribution, we want the probability that k minus 1/2 is less than or equal to x is less than or equal to k plus 1/2. Now we call this the continuity correction. And notice what we've done. We've taken, instead of being x equal to k, we've sort of put an interval above and below, right? K plus 1/2 and k minus 1/2. And we've centered it at x. Now remember, the discrete random variables, they only take on integer values, whereas continuous random variables, they've got 0 probability at an exact integer. So that's why we've got to create this interval around k so that we can approximate that probability with the normal distribution. Great. So what's our next step? Well, remember when we started to standardize random variables? Well, that's exactly what we're going to do here. Here you see we've subtracted out the mean, which is n times p for that binomial. So the probability of k minus 1/2 minus the mean is less than or equal to x minus the mean, which is less than or equal to k plus 1/2 minus the mean. So you know what we have to do next? We have to divide out by the standard deviation, which in this case is the square root of n times p times 1 minus p. So notice here we've gone through, subtracted our mean, and divided out by the standard deviation. So what is that new random variable that we have in the middle? It's a standard normal. We can write this as now the probability that k minus 1/2 minus np over square root of np1 minus p is less than or equal to z, which is less than or equal to k plus 1/2 minus np over the square root of np1 minus p. Now, this distribution is familiar to you because it's the standard normal distribution. And all we've done is standardize our binomial. So now we want the probability that x is greater than k. This translates to, for the normal side, the probability that z is greater than k plus 1/2 minus np over the standard deviation, square root of np1 minus p. But we know what x is. X is binomial of 3010.6, and z is a standard normal. So let's plug those values in now. The probability that x is greater than 1850 is equivalent to the probability that z is greater than 1850 plus 1/2 minus 1800, which was the mean of that binomial, divided by the standard deviation, which is the square root of 720. This gives us a probability that z is greater than approximately 1.88. Now, we've solved these in R before using the p-norm, and all we have to do is plug in p-norm of 1.88, 20239. But remember, the lower tail has to be false because we're looking for that upper probability. Here's what happens when we plug that into R. We get a value of 0.0299 approximately. So there's a 2.99% chance that we have more than 1,850 fans in attendance. All right, I know you're probably thinking, what would we have gotten had we actually used the binomial calculation? Maybe you've actually gone out and done it. What'd you get? Well, we can use R to do the exact calculation for the binomial. And it's called the p-binom. But in this case, we want to subtract. So 1 minus the probability of binomial at 1850 with an n equal to 3000 and a p equal to 0.6. Look at that value that we get. It's really close to what we got in our simpler approximation with the normal distribution, 0.0296. You might be asking yourself, what if I didn't do this continuity correction? What does this adding 1/2 and subtracting 1/2 do anyway? What if I just wanted to standardize and plug it straight in to my normal distribution? Well, if we do that, we get a value of 0.031 approximately. And notice how we're slightly off. The actual binomial value was 0.0296. Our normal approximation with the correction, where we added 1/2 and subtracting 1/2 and centered our data right there at x equal to k, gave us a closer value of 0.0299. And notice that if we did that normal approximation without the correction, we would have been even further away from our binomial at 0.0312. Now, often when I consult with researchers that are designing an experiment, one of their top priorities is keeping costs down, which translates to them wanting to take fewer samples and somehow magically invoke the power of the central limit theorem. But unfortunately, it doesn't work that way. Unless you know that your true population is normally distributed, then you'd need at least 30 or 40 samples before the central limit theorem is even going to kick in for you. The central limit theorem is an important concept that lets us approximate the sampling distribution of X bar with a normal distribution. But if your data has extreme variation or several outliers, then you might need an even larger sample size.